Decided not to use slides for this talk. As you probably know, I've been working on AT for many years, most of the time in Israel, and I think I've known most of the Israeli AT families. I met a few of the UK families over the years, but this is the first opportunity I'm given to talk to this audience, and I'm very grateful for this and appreciate it very much. I wasn't sure what type of talk to prepare, and that's why I didn't actually prepare any slides, and I thought I shouldn't get into the details of the science, but rather give you the basic concept of what we're trying to do now. So our philosophy over the years has been that we should understand the disease, the physiological and molecular basis of the disease first, and then based on that understanding try to either do it ourselves or help others find ways to treat the disease based on that understanding. And I think that the field, which means not only us, of course, many laboratories, indeed has reached this point now. There are still a few open questions, and in science there are always open questions, and in fact you answer one, you get it just opens the way to 10 new ones. And we've just spent 2 wonderful days here discussing the meeting point between the basic science and the clinical science and treatment of the patients. And indeed, there are still open questions. And I think that even you here at this meeting, just listening to the various speakers, will notice the different nuances and different viewpoints, particularly about the main feature of the disease, which is the neurodegeneration, the cerebral degeneration, which is obviously, speaking in clinical terms, the essence of this disease and the most important feature which we want to treat first and foremost. So this means that we have to understand, of course, each and every one of the symptoms of the disease, of which you're all very, very much aware, more than anybody else, but particularly, probably first and foremost, the neurodegeneration. And actually, trying to understand this cardinal feature of the disease is where there are still many open questions and differences of opinion, differences in findings. And what we're trying to do, and that's why we meet so frequently, there are very frequent meetings, scientific meetings in this field, which is very good. But you know, the last AT workshop took place a few months ago in India. We met here. We will meet actually in this country again next summer for the AT workshop, next AT workshop in Birmingham, which is good because each of these meetings allows us to discuss these open questions again and make some steps forward. And we do make a step forward in each such meeting. So that's really good and very rewarding. So we have our own view, which we are still actually developing on the molecular basis of the neurodegeneration in AT. And I should stress again that this is still an open question, and even we are still elaborating on this and develop this further. It's sort of an evolving process, and this is very typical of any scientific process. You ask a question, you do an experiment, you get an answer, which either confirms a hypothesis or doesn't confirm, and then you have to think of a new hypothesis. And like I said, these meetings and exchange of views and information, which is, again, very, very good and efficient in this field. So the interaction between scientists is really excellent and has always been excellent in this field, and this is really a blessing. It's not like this in many other fields in the life sciences, I can tell you. So what we're trying to do is the following. We think at this point that most, if not all, of the clinical features of AT, including the cerebellar degeneration are related or result from the loss of a basic function of the ATM protein, which is the product of the AT gene, ATM, which is related to, as you probably all know, the maintenance of the stability and the integrity of our genome, the DNA. You probably heard a lot about this in many meetings, and it will be mentioned again and again today. There are other functions for the ATM protein. Actually, it's quite an amazing protein. It can do a lot in the cell. It can activate very complex processes, and it does so by interacting with many other proteins, and not only interacting with them, but it also can modify them chemically. It has this ability to induce very subtle chemical changes in other proteins. These are very subtle changes, structurally speaking, but they can have a huge, huge effect on the activity or the stability of those other proteins. And those other proteins turn out to be key players in many processes in the cell. So when ATM acts on them and modifies them, it thereby modulates and changes many processes in the cell. So you can regard it as like a master regulator of many processes in the cell. And it does so, among others, in response to specific types of DNA lesions, DNA damage, mainly those that are caused by ionizing radiation, and that, of course, explains the acute radiation sensitivity of AT patients. So it is actually the master regulator of the responses to a specific DNA lesion, which is not the only one induced by ionizing radiation, but certainly the most dangerous one, and that's the one that Dr. Gatti alluded to, the double-strand break. And we know a lot, but still have a lot to investigate about the way that, by which ATM gets activated, comes into action following the induction of such lesions and so forth. And we think it has, beyond activating this very complex system, it has many other roles in maintaining the stability of the DNA in many other ways, in the face of the ongoing damage which is inflicted on DNA. In fact, as you know, in the lab we use cultured cells and we treat them with ionizing radiation, and we see the activity of ATM, and of course in AT cells we don't have these readouts because ATM is not there. But you might be wondering if this is at all relevant to what's going on in everyday life, because most of us are not irradiated unless it is absolutely needed, and certainly not AT patients. So we think that in addition to activating this enormous system in response to this very critical DNA lesion, ATM is involved in many ways as sort of a background player in the response to many other types of DNA lesions and abnormal structures which happen all the time, which are induced all the time in our DNA without being irradiated. Everybody who is sitting here in this room, in each cell of our bodies, the DNA is being damaged all the time. And the reason for that is that some of the byproducts of our normal metabolism damage the DNA. So fortunately, most of us have these very efficient defense mechanisms. And of course, AT patients lack one of them, which is activated by the ATM protein. And that's why ATM is such a disease that progresses all the time, even without being exposed to any ionizing radiation, nothing of the type that we do in the lab. That's because of this damage which is induced in the DNA all the time in each cell of the body, and that's natural. It's byproduct of DNA metabolism. So while healthy individuals can defend their DNA against this ongoing attack on the DNA, AT patients cannot do it very efficiently, and that's the reason of their disease.